This class will continue the discussion on the design of computer instruction set. So far we have seen the what is the format of a computer instruction, what are the two parts or two fields of a instruction, and how the opcode part, the instruction opcode is encoded. And then we introduce the reduced set instruction computer, and what are the different RISC machines so far developed. Now, already I mentioned that nowadays almost all the high performance computers are the RISC machines. So, just to see what are the basic architecture of RISC, some early machines developed based on RISC, we will see that thing. So, some early RISC projects are IBM machine and the Berkeley RISC-1 and RISC-2 machines and Stanford MIPS. So, this class we see as an example the MIPS architecture. So, the MIPS instruction formats, that all MIPS instructions are 32-bit long. So, this is the instructions are 32 bits. The three instruction formats are R type, I type and J type. So, it supports three different instruction formats, and the different fields are op means operation of the instructions, that means which operation are supported or which operations are currently being executed by the instruction. RS, RT, RD, the three source and destination register specifiers. Then shift amount, SHAMT is a shift amount, that is a different field kept in MIPS. Another is funcT, it selects the variant of operation in the op field. Then address and immediate, that means address offset or immediate value, that means the data, or this is some kind of mode of operations, that whether it is the immediate value is being operated on, or the address is given or address offset, and from some addresses the data had to be accessed before it operated on. So, these are the different fields that are kept on the early MIPS machine. Now, these are the three type of the instruction format. So, all are of 32-bit long. So, see here this is the first type, that 6 bits are the operations, which operations. RS, RT, RD, these are all, everyone is of 5 bits, means these 15 bits are for the registers, the source and destination registers. Then this is a shift amount, is again 5 bits, and this is a funcT, this is a 6 bit. Now, another instruction format is 6 bit is of opcode, operation field. Then only RS-RT 2 registers are kept instead of 3, and these are 5 bit. Rather immediate value, that means 16 bits are kept for immediate. So, here that value is immediate value is can be taken. So, that is why the 16 bit data, this is actually the 16 bit data. Now, another one is that this is totally the address field based. So, what actually initially we introduced the instruction format is of opcode field and the address field. So, the third one is the classical in nature. So, 6-bit opcode, that means 2 to the power 6 or 64 such operations are specified, and 26-bit address, that means 2 to the power 26 locations are available to keep or to store the data to be operated. So, this is the thing. So, this is our in the simple instruction format that has 2 field, opcode and address field, that this is the instruction the MIPS supports this one. This is some a different type, that as if that values are stored on registers, the immediate values, and that can be taken from this 2 to the power 16. The immediate values can be taken from here, and in that way it can be worked on. Now, the MIPS instruction layout, these are of standard. So, this is actually taken from the Elsevier Science USA, because this is already implemented. So, what layout they have fixed, they designed, it is taken as it is given as an example. So, this is the I type of instruction. As already we mentioned, they propose 3 type of instructions format: I type, R type and J type. So, I type means the immediate value type. So, already we have seen that I type is opcode, RS, RT, immediate. So, it encodes loads and stores of bytes, half words, double words and all immediates is RS to RT of immediate. That means, here the operations type is of it has these 2 type of RT opcode, RS RT are the source and destination registers, and the immediate type. So, opcode 6-bit, 5 RT RS 5-bit, and the rest are immediate value. The 16 bits, because total is 31 bits. Now, here the operations are of the 2 registers, it is a load store type, that RS the operations immediate means whatever the immediate value is taken, the operation is on the content of these registers. This is the register value, this is the immediate value, and they two are operated and moved to the destination registers. So, this is the type of operations, the I type. So, this is the I type operations to be performed, this is the I type. Now, conditional branch instruction, RS is registered, RD unused, and jump register, jump and link register. R type instructions, here that opcode RS, RD, that shift amount, SHMT and func. So, register ALU operations is RD, RS, func, RT. So, here the operations is the between 3 registers, it is between 3 registers, that this is R type. The operations are RD is RS, func, RT. See, these are again 2 registers, content of 2 registers functions, and then it is operated on that, it is value is moved to RD. Function encodes the data path operations, add, subtract and read write special registers and moves. And J type is simple, the opcode and offset added to PC. So, jump and link, trap and return from exception. So, these are the 3 instruction formats initially proposed by MIPS. Now, MIPS addressing modes or instruction formats. So, this is called a direct, the register. Direct mode, the 6-bit opcode is there and the 3 registers RS, RT, RD. So, RS is taken as if the register. Now, immediate means that already we have seen that always the data is the immediate value is operated with the content of RT and then shifted to RS. Then some displacement. So, here see immediate value and the RS register, RS RT are registers. So, content of these registers, this is being operated and then that it gives the address of memory. So, this or immediate can specify the displacement. So, this is another facility or some flexibility has kept of this type, that I type. Here immediate is not the data, but the immediate gives the as if the offset value, the address offset. Now, PC relative, that is the program counter and the immediate value, and it always gives the memory location, and here all instructions are 32-bit wide. Now, how the instruction sets are designed. So, it used general purpose registers with a load store architecture. This is the basic principle of RISC architecture. So, this is the basic principle of RISC architecture is load store. Provide at least 16 general purpose registers plus separate floating point registers. So, it keeps a number of registers. So, 16 general purpose registers and also some floating point registers are kept. It supports basic addressing modes like displacement, just now we have seen, with an address offset size of 12 to 16 bits, and the displacement value is taken from the immediate, the 16 bit. Immediate size 8 to 16 bits and register deferred 16 bits from immediate displacement. All addressing modes apply to all data transfer instructions. It uses fixed instruction encoding fixed instruction encoding if interested in performance, and use variable instruction encoding if interested in code size. So, again it is a flexibility kept. Normally RISC is told that fixed instruction encoding, but if needed it has some variable instruction encoding is also kept if the code size is to be considered. Then it supports these data sizes and types 8 bit, 16 bit, 32 bit integers and 32 bit and 64 bit IEEE 754 floating point numbers. It supports these simple instructions since they will dominate the number of instructions executed. The load, store, add, subtract, move, register to register, and shift, compare, equal, compare not equal, branch with a PC relative address at least 8 bits long, jump, call and return. So, it has some other miscellaneous instructions, but mainly the main instructions are load, store, add, subtract, and shift, some compare, some branching, that means jump type of instructions, then call and return. Aim for a minimalist instruction sets, and from there they are selecting a basic instruction set and they are implementing these instruction sets. So, mainly the reduced instruction set, the concept comes from here, the minimal list of instruction sets that are needed. So, the approach is like that. Now, RISC is a 5-stage execution. This is already we got told that this is a load store architecture. Now, this 5-stage are instruction fetch, instruction decode, execute, memory and the write back. What it does, instruction fetch, it get instruction from the memory, that which instructions to are now is to be executed. So, first it fetches the instruction, then instruction decode, register read. So, instruction decode that what is that instruction, translate opcode into control signals and read registers. As already we have seen one example that every instructions or the opcode field is actually encoded with some binary numbers. So, decoding that binary numbers, that which instruction actually it is, means the instruction decoding. So, we have done the opcode encoding, now the reverse thing we will be doing, that decoding the instructions, seeing the binary numbers assigned to the opcode field. Now, execute, this perform ALU operation and the load store, addresses, branch outcomes, that means whatever instructions is supported by MIPS, it will be executed by this stage, in this stage execute. Memory, memory means this accessing memory if load store and else everyone else idle. Another is a write back. Now, another very unique concept and that is very important thing, that pipeline concept now has come into picture. Now, concept is actually the overlapping or overlapping execution of instruction, or we can tell the utilization of overlap execution of instructions is called the concept of pipeline. What is that? The start instruction on every cycle, the new instruction can be fetched while the previous one is decoded. So, this is one stage of pipeline. Each cycle performing as a specific task, number of stages is called pipeline depth. So, already we have seen it has 5 stages: instruction fetch, instruction decode, execute, memory and write back. So, for one instruction, say for one instruction we are doing, we have already done instruction fetch, and now for the second instruction, say already it is fetched for first instruction, then it should be decoded. It has, the first instruction is already. So, for first instruction what we can tell, when it is instruction fetch has already done, it is over, then it is instruction is decoded. Now, for the second instruction it can be a instruction fetch. So, when the first one is decoded, that time the second one is being fetched. So, this is some overlapping of operation. So, this overlap of execution of instructions, that is called the pipelining, and every cycle performing a specific task or number of stages is called a pipeline depth. So, here actually this is a 5 tasks are there, 5 stages. So, that is called the 5 here. So, this is a we have given here time scale, the time axis, as if this 1, 2, 3 up to 15 time steps we have shown, and this is the 5 stages: instruction fetch, instruction decode, execute, memory and write back. Similarly, this is for another instruction, again that 5 stage, another 5 stage is kept. Now, see, if it is a non-pipeline, that means for every instruction, when the, say the first, if this is the first instructions, then all the 5 stages should be executed, and then only the second instruction can be processed. Again, unless the third instruction cannot start the processing unless the second one is finished. So, this is, we can tell that the sequential execution of the instructions one by one, the instruction 1 first, then instruction second, then instruction third, like that. This is called the non-pipeline. Now, the concept is as if the execution of one instruction that is being divided, that is partitioned into 5 stages, that fetch, decode, instruction fetch, instruction decode, execute, memory and write back. Now, see that for the first instruction, say this is for the first instruction, the instruction fetch is already, it has been done. Now, for the first instruction, this is for the first, the instruction is being decoded. Now, when it is being decoded, then the second instruction is already in processing stage. So, for the second instruction, the instruction is being fetched. Now, at the third step, means third time unit, the first instruction is being executed, and then the second one is in instruction decode stage, and that time already third is also in process. The third instruction already is in process, and now it is in instruction fetch. So, as if the first instruction is one time step in advance with respect to the second one. Again similarly, the second instruction set as if one time step in advance with respect to the third instruction set and so on. So, this is this overlapping, say here the second time unit to the fifth time unit, the first instructions and second instructions are being overlapped. Similarly, from third time unit to the sixth time unit, the second instructions and the third instructions are in overlap and so on, if there are more such instructions in queue. So, this is the concept of the pipeline architecture, and this is being employed or utilized in RISC. So, if we see that the actual architecture of this pipelining, say these are here, this is a instruction fetch or instruction decode and instruction execute. There is execute and memory, and this memory and write back. So, as if see if we just see that thing, so as if here here at second time stage these two are overlapped at, so ID instruction decode and instruction fetch. Similarly, at third time step instruction decode and instruction execute, and as if these are come here, this is IDIF, this is IDIF, instruction decode, instruction fetch. Similarly, at fourth time state memory and execute, they are overlapped, and fifth time step that write back and memory, they are overlapped. And see, this 4 overlapping is also here, IDIF, EXID, execute ID, memory, execute, write back memory. So, actually there are 4 overlapping stage. Now, as if we are partitioning the at each partitioning the time units, and at each time units which stages are being overlapped. So, there are 4 overlap, and these overlapped are being shown. This is IFID, the overlapping of fetch and decode, overlapping and decode and execute, overlapping of execute memory, overlapping of memory and write back. So, see, this is the program counter, some multiplexer is there. This is instruction memory. So, from this instruction memory, instruction is being fetched, and as the instruction program counter is incremented by 1. Then it goes to some, these are some register files. So, it goes to the after instruction fetch, it goes to the decoding phase. Okay. So, instruction decode. Now, again this is after decoding, that what type of operation it is. So, it will be execute. That time that say memory is also from data memory, the data is being taken from the memory, and then it is a write back. That means, again the result is stored on the memory, or the data being updated on the memory. So, this is one stage. Now, when one instruction has advanced one time step, that means the instruction decode, then from the instruction memory. So, this is the first instruction, and now it has come here. Now, the second instruction is being fetched, and then it is being So, when it is being decoded, then it is second one is fetched. So, this is the overlapping region, and in this way it will proceed for other instructions also. Now, a pipeline with multi-cycle floating point operations. Say we are only the two stage we are considering. Say this is first this is a instruction fetch and say instruction decode. Now, so two operations are shown here. One is multiply, the mult, and here this is a adder, addition. So, this is our execution mode EX. This is the execution phase. So, the first instruction is fetched, decode, and it is being executed. Say it has a multi-cycle operations. Say for multiply we need M1, M2, 3, 4, 5, 6, so 7 cycles. Similarly, for addition, say there are 4 such cycles A1, A2, A3, A4. So, when one instruction will be in process, that means it will be in advance with one cycle, then the next instructions can also be processed for these floating point operations. So, here actually these cycles or this can be a pipelining stage for this floating point operations. This is a multi-cycle floating point operations. Now, here the data memory is accessed, this is a memory operation and then it is a write back. So, this is one example of a pipeline with multi-cycle floating point operations. Now, there are some problems associated with pipelines. Normally, we call that are hazards. Hazards are mainly these are some problems to be tackled when we when we use the pipeline architecture. So, hazards are caused by conflicts between instructions which will lead to incorrect behavior if not fixed. So, these are some problems to be handled, and as pipeline is a gain that we are actually employing the overlapping stage. That means, when one particular instruction is in one stage, say it is instruction decoding, then the second one is started its fetching part. So, that is the advantage we are doing, that in this is there are some overlapping stage. Now, for that there can be conflict because two instructions are processed parallelly, at least two. There are some stages where the instructions are, say we have seen that here there are, so this is a overlapping stage, this is a overlapping stage where three stages are actually overlapped. first instruction is in execution, second instruction is in instruction decode stage, whereas the third instruction is in instruction fetch. Similarly, at the fourth time step also there are overlapping of 3 stage. So, at the 3, 4, 5 time steps, these are, say, this is a 3 stage overlapping of 3 stage. So, these time steps, that means at 3, 4, 5 steps, at 3, 4, 5 time steps or time units, more than one instruction is in process. Are in process, either fetch or decode or execute or memory and write back, different type of stages. So, what will happen, that as more instructions are in process, this is the main point. So, their instructions can access the same data or the same register value. Then what will happen? If parallelly that more than one instructions access the same thing. So, the main problem or the main hazards means that this is the problem if more than one instructions want to do the same thing. So, hazards are caused by conflicts between instructions. It will lead to incorrect behavior if not fixed. So, normally there are 3 types of hazards: structural hazard, data hazard and the control hazard. Now, what do we mean by structural hazards? The 2 instructions use same hardware in the same cycle. This is called a resource conflicts. Say one memory port or unpipelined divider, etc. Say one operation unit, say one multiplier or one divider is there. Now, 2 instructions want to use or want to employ the same unit, or say one memory cycle, same cycle. That means, the same hardware unit being requested or being used by the 2 instructions parallelly or at the same time, same cycle, then it is called a structural hazard. Now, data hazard. Now, 2 instructions use same data storage, register or memory. The data is stored either in register or in memory, and 2 different instructions, because they are in process, and that is the concept of pipeline. So, the operations are such that both the instructions use the same data storage, then it is a data hazard. Now, the control hazard, that one instruction affects which instruction is next. So, PC modifying instruction changes control flow of program. So, this is also a one type of hazard called the control hazards. Now, how to handle the hazards? So, there are mainly 2 things to be implemented. One is force stalls or bubbles in the pipeline. So, if the first the intuitively what it thinks, that if more than 2 instruction want to get the same resource, hardware or data from the memory, then actually hazard comes. Then what we can do, we can stall one, that means one will use that thing and one will stop its using, then hazards can be controlled. So, these 4 stalls are bubbles in the pipeline. So, stop some younger instructions in the stage when hazard happen. That means, as if the anyone, say we are calling younger one, that next one which just comes later, that instructions accessing is being stopped, whether it is a hardware or whether it is a data resource from memory or register. Make younger instruction wait for older ones to complete. Again, that stalling means that actually it will wait for some predefined time, or it will wait for some time until the first one completes its use. Then in that way we can handle the hazard. And deassert write enable signals to pipeline registers. This is called the implementation. That means how it is being implemented, the hazard handling hazards. Then it is some write enable signals to pipeline registers, that in that way it can be implemented. Another is flash pipeline. So, blow instructions out of the pipeline. That means pipeline means some overlapping of some stages. So, if this hazard occurs, that means just flash out, as if one stage means one temporary time units, as if at that time unit some of the instructions are being thrown out. Refetch new instructions later, solving control hazards. So, these instructions are again refetched, and assert clear signals on pipeline registers. So, this is how it is being implemented, that clear signals on pipeline registers are being implemented just to implement the flash pipeline concept. Just like the 4 stalls, that it is DS write enable signals to the pipeline registers are implemented to get the 4 stalls bubbles in the pipeline. Now, we see how the structural hazards are dealt. See that it is a stall, if it is a stall type, so it is simple, low cost in hardware and decrease the IPC. Replicate the resource, so good for performance, increase hardware and area used for cheap resources. So, replicate the resource, because 2 instructions parallelly want to use the same resource, but we have only one resource. So, one solution can be that replicate the resource. So, obviously, it will be very fast, because there will be no hazard is control, and the performance will also be good, because parallelly or at the same time both are using the resource. But replication means that it will increase the hardware, and obviously hardware means it will be the increase the area, but speed wise it will be very good. Used for cheap resources. So, it can be a good solution if the hazard occurs for some cheap resources. Say that nowadays the hardware, say memory, this is a very cheap one. So, if the two for some instruction they want to use the same memory, then what we can do, that we can replicate this one. So, this will be a good solution. Now, pipeline the resource. This is good for performance, complexity, and again for restricted RAM, that only that RAM is there. So, it will be a good use. Useful for multi-cycle resources. Just now we have seen one multi-cycle floating point adder and multiplier. So, for that type of structure, for that type of machines, that if two instructions want to use the same floating point unit and the hazard occurs, then if it as it is a multi-cycle, then always what we can do, we even that cycles that can be pipelined. So, that for not only that overall pipeline concept, this is a nested type of thing, that for floating point units, that whether it is a floating point multiplier, floating point adder, as if the cycles are also pipelined between the resources, pipeline the resource, as if these are the resource and it is pipeline between the two instructions. So, this can be the solution. So, here actually we have shown that if this type of hardware is there, that everyone is using that, and then this can be easily pipeline. Now, the data hazards. So, two different instructions use the same storage locations. Data hazards means this is that either same storage locations either from memory or the registers. Now, there are different cases we see. It must appear as if they executed in sequential order. So, two different instructions use the same storage locations. See, one memory operation means always the memory operations are only two. Already we have read the memory, the ROM, the RAM, and we have seen actually there are two operations, read and write. That means only the memory is access, always it is accessing the cell, the data, or the data is kept or stored. So, see, this is what we are seeing, this is one type of, so this is a add R1, R2, R3. So, the registers values are added. The next instruction is subtract R2, R4, R1. See here that both the content of, see, the R1, R2 are common, here R1 and R2 are common. So, and they are subtracted and then kept, or R1, R6, R3. See, here it is a R1 add. So, first the two values are read, the values are added, and then it is kept. So, here it is a write is also there. Now, between this addition and subtraction, actually it is a read, subtraction, the value will be read after this write. That means, in subtract this instruction, in subtract instruction there will be a write after a read operation in the add instruction. So, here the two instructions add and sub, they use the same storage R1 and R2. Now, is there any conflict? Because both are using the same storage R1, R2, the two registers, but here subtract, it is a read which was written in the first instruction add. So, this is a read after write, we can tell this is a read after write, and this is a true dependence or real. So, there will be no problem, no hazard here, hazard is control. Now, next one, say add R1, R2, R3 and say this here R1, this R1 value was here. Now, R2 is subtract R2, R4, R1. So, that means, here this is a write after read, because here also the R1, R2 are common registers, R1, R2 are common registers, and in the first instruction add, the value is read R2 and that is being updated in the second instruction. So, this is a write after read, and this is anti dependence. So, this is artificial. Similarly, the third one, say here add R1, R2, R3, subtract R2, R4, R1 or R1, R6, R3. So, here R2, R3 value, that is added and kept in R1, and again OR R6, R3 is ORed, kept in R1. So, R1 is write after write, that is in the first instruction and the third instruction add and OR. So, again this is a write after write, this is also output dependence and this is artificial. Another one is there, that is called the read after read. So, read after read, as normally this is not a problem, because unless we write something, that it will be of no, it will not create any hazard. So, these are the part of data hazards. Now, the control hazards. So, this is a branch problem and branches are resolved in X stage. So, 2 cycles penalty. So, this is a branch problems and solutions are reduce branch penalty. So, change the data path, new add are needed in ID stage, the instruction decode path, fill branch delay with a useful instruction or fixed branch prediction or static branch prediction or dynamic branch prediction. So, using these solutions control hazards can be handled. So, mainly in this class what we have done, we have read the reduced instruction set architecture. We have seen that for mainly one pipeline operation can be implemented, that is a very big advantage, but for pipeline there can be some problems called the hazards, the structural data and control can be there, and how these hazards can be controlled, that we have seen. So, now the lecture 34 quiz, I am giving one problem. Already we have seen that how it can be designed. Actually, in the next class we will see that how the arithmetic logic unit will perform the functions. So, actually in the next class we will be seeing that how the ALU can be designed. This is a part of a CPU design. So, we will end the class here. We are reading the design of computer instruction set and the CPU. In the last class, we have seen that how the computer instruction set can be designed, and the reduced instruction set machines, then the current state of the art, actually all the machines nowadays are reduced instruction set. So, how the instruction set are selected, how it can be designed, how it is what are the hardware implementation of it, that already we have read. Today we will start discussion on the design of CPU, and first we will see the design of ALU in this class. So, CPU contains 3 elements: the registers, the ALU, the arithmetic logic unit, and the control unit or CU. Now, already when we have discussed, we read the different type of register designs. There we have seen the how shift registers can be designed using flip flops. The barrel shifter, or what we can tell that this is actually a more than 1 bit transfer, that called the barrel shifter, the 4 by 4 or 8 by 8 barrel shifter, 16 by 16, how they can be designed, already we have read that part. Now, the arithmetic logic units, as its name implies, the arithmetic units. So, it has actually 2 parts. One is the ALU design, the arithmetic unit and the logic unit. Now, the